All right, I think it's time. So welcome everyone to this session about designing software with security in mind. I'm so happy to see that there's so many people interested in security and also how you can design software that meets these security requirements that we have out there today. Short notice about me. My name is Deogun. I'm from a company called Omega Point in Stockholm, Sweden. I'm a senior consultant there. Started to play with Java back in '97, worked in various domains, of course in medtech, telecom, gambling, web. And as it turns out, I'm not one of those typical security people. I'm actually more of I'm a developer with a security mindset. And you will soon learn about this in this talk. And I'm a strong advocate of domain-driven design, test-driven development, and something called domain-driven security. And of course, I'm really passionate about high-quality software and design. And well, enough about that. Let's dig into the fun stuff in this talk. Well, throughout the years, I've been working in various projects where we have had these type of security requirements that, we have a really sensitive data and it should not be exposed to malicious attacks, of course. And throughout the years, I've been setting up this hypothesis, and it says crafting software with good design principles along with a security mindset significantly reduces the number of security flaws in an application. And at first that might seem trivial, but the fact is that we have so many security issues out there, so it's really a question if this is true or not. So we'll see what happens after this presentation, if we can prove this. So in order to find out if you can actually write secure software, we need to ask ourselves a few important questions. And the first one is, of course, what distinguishes secure software from insecure software? Are we able to look at a piece of code and determine that, you know what, this piece of code is secure. This has secure properties. This looks like this is very good code. This will not be vulnerable to these kind of attacks. Or is this actually not possible? So we'll see. Another question is, of course, legacy code. Adding security to new greenfield project is probably very easy. But how do we deal with the old stuff we have out there? Can we make old legacy code secure? I don't know. Another thing is, of course, is it really possible to design secure software? The hackers out there are really, really good at what they do, right? So they come up with all these weird stuff, and they seem to go around things, and all suddenly we're standing there with our pants down, and we have to be embarrassed that we have added this security flaw in there. So the question is that, is it really possible to design secure software after all? And of course, the toughest question of them all is that, is security a quality aspect, or is quality a security aspect? I don't know, think about that one. Okay, so for our help in this talk, we're going to look at something called OWASP. How many of you know about OWASP? Oh, great. That's quite a few. It stands for Open Web Application Security Project. And they actually have this list of various security flaws out there that seems to be very common among web applications. So if you are a web developer, you should definitely know about this, because this is something that you need to handle in your code. Unfortunately, we won't be able to cover all of these in this session, but I've decided to focus on two of them. And one of them is, of course, number one, injections and injection flaws, and the third one, cross-site scripting. And you'll soon realize why I've picked those two. Well, the first one, injections. So if you look at the documentation, it says injection flaws such as SQL, OS, and LDAP injection occurs when untrusted data is sent to an interpreter as part of a command or query. The attacker's hostile data can trick the interpreter into executing unintended commands or accessing data without proper authorization. And then you go like, wait a minute, what does this really say? It says untrusted data trick the interpreter. That's really what the key messages in here. And you go, I don't have untrusted data. Well, no, the common user doesn't, right? I mean, they use the system as intended. But there are so many evil people out there, and they try to inject stuff into your code and make your system behave strangely, right? So the best way to illustrate this is, of course, through an example. Assume this is some sort of web form, and you are supposed to register an address. And as it turns out, this is the address to Omega Point in Stockholm, so in case you are over there and visiting, so you can find this out. So you enter the street name, number, zip code, city, and the country, of course. And well, you're all fine. And if you look at the code looks something like this. It takes, a street, number, zip, city, country. And we're all fine. All suddenly, we get these reports saying that, you know what? We've been seeing some really strange behavior. It's either crashed, or all suddenly, we got notice that all our address records went public. How can that be, right? And then we start looking at the logs and whatever we have, and we start realizing, like, wait a minute, there's some really strange access going on here. And then if you look at this code and try to figure out what are the different ways we can actually do attacks in this code. So let's look at some illegal input here. The first one is very simple. Since we are using strings, we can actually swap them, right? From a compiler perspective, making the city called Sweden or the country called Stockholm isn't any different. The compiler is not going to complain. But from our perspective, that's wrong. And an attacker can, of course, inject these parameters in whichever order they want to. Another illegal thing could be null parameters or even a SQL injection. Actually, it's illegal data. So we inject illegal data at these various parameters, and we can make the system behave strangely. Third one, unbounded input or very large input. That's very funny. You know what? If you accept a string and there's no boundary checks, all suddenly that system can just go banana. Because you got a string that's so big, it basically fills up the entire heap. And, well, that's funny. So what should we do? Well, one way is, of course, to treat this as a validation problem, right? We want to make sure that we don't accept any illegal data. Sure, that's one way to do it. So we basically would create a strong security barrier around our application, saying that at every entry point, we are going to validate the data that gets in there. And if that's okay, we're going to proceed. If not, we're going to reject it. And of course, we're going to use whitelist input validation, which means that we are going to focus on the things that we accept. Everything else is by default rejected, right? So if we look at our code again, we will have something like this. If you pick the street there, for instance, the top one, we say, well, the street cannot be null. The length needs to be to a maximum of 100 characters, apparently. And then we need to match this pattern of A to Z, and then there's some Swedish characters in there and a space. And it needs to be at least 3 characters long. And the same thing goes with the street number and the zip code and so on, and some additional validation. And if we go through all of this, we say, check, we're okay. Now we can actually move on and use these parameters. Right. So what's the problem with this? Well, first, the upsides are, of course, that we prevent illegal data from being processed. That's good. And another thing is that we detect it as early as possible. Wow. And we focus on the illegal input values. But the downsides, and these are important to know, is that we apparently seem to separate validation and data. If you looked at the code, we had our validation block, and then we had our data, the usage of it. And this actually tends to make duplications, because if you enter addresses as various points of your application, that validation logic is probably duplicated. And at first it will work fine, but after a while, you start changing one validation in one place and something in the other place, and all suddenly you have holes, and you actually have possible flaws in there. But that's not really the major downside. The major downside is that this tends to focus on structural correctness. Is the number correct? Is the zip code correct? Is the city name correct? And so on. And we tend to ignore or forget to check the invariants. And this is something I call a second order injection flaw. And this is my saying. So I claim that an attack vector which structurally correct data that exploits missing invariant checks between input parameters or application state. That means that if you can inject something that is structurally correct, but it violates some sort of invariant check that should have been there, we can actually exploit that. So an example would be this. This address that we send in here is structurally correct. But the problem is that there's actually an invariant between the zip code and the city in Sweden. The first 2 digits in a zip code in Sweden is actually a numeric reference or mapping to the city. 11 turns out to be Stockholm. So that's the postal code for Stockholm. It starts with 11. It actually can start with 10 and all other numbers too. But Gothenburg is not using 11. So this address is structurally correct, but if somebody hacked this and injected this as your shipping address, every time you add something to your basket, all the stuff that you added there and you paid for gets shipped to somebody else, if that's a valid address in Gothenburg, right? Maybe not because of the zip code, but the delivery guy is going to go, I'm supposed to deliver to that street, that house number in Gothenburg. Fine. Yeah, let's do that. I'm not going to check the zip code invariant. Right? They only look at the address and go like, fine. I'm in the right country as well. That's good. So how should we deal with this kind of things? Well, as it turns out, like I said in the beginning, there's something called domain-driven security. And unfortunately, I wasn't the one who came up with the idea. Instead, it was actually my colleague, or actually my colleagues at the time, Dan Berg-Johnson and Dr. John Wilander. They actually introduced this at Java Police, which later became Devox. So it's kind of funny. But that was back in 2006. And the core essence in this is that they brought in the power of domain-driven design into the realm of security. Right? And what they did was that all the input data, it should be mapped to value objects in the domain. How many of you have heard about domain-driven design? Oh, a few hands. Good. Okay, so the key here is that it actually combines structural correctness and invariance checks, and validation and data is kept together. And let's look at how that actually works. But since we are moving into domain-driven design here, we need to actually get a notice of what does an address mean, right? Remember, DDD is all about understanding the domain and moving that into your code. So if you think about an address and you're going to go for a job interview or something, you would go like, yeah, this is probably a geolocation. I'm supposed to go to that street in that city in Stockholm, in Sweden, to house number 56. That's really the conceptual way of thinking about an address. The delivery guy or postal service will actually use the zip code as well. Perhaps not the delivery guy, but this postal service at least. So that's how they look upon addresses, right? So based on this information, we would of course create a model. That's how we would do it as developers. So we create this model, and except for all those structural correctness that we need in each particular component, we will actually add these invariants to this. So in order for an address to be correct in our conceptual way, we would say that the city must exist in that country, right? Stockholm must exist in Sweden. Makes sense. The street must exist in the city. Yep, that is also something that needs to be correct. The building, a building with that particular number must exist on that particular street. If it doesn't, Well, that's an invalid address. And of course, the zip code and the city must match. Otherwise, that address is flawed. And this is really hard to just do structural validation. So instead, we would use our code, and this was the code that we used for the structural validation. Let's see what we do if we brought in domain-driven design and domain-driven security. You would say that every input data should have been mapped to a value object in the domain. And the value object, let's say zip code, would do this. Say we have a zip code there, it takes the string value as a parameter in the constructor. It validates that, well, that's the same structural validation, right? See, if I move back one, you see that's the structural validation of zip, the third one down there. And if it's accepted, we know this is structurally correct. And it's actually immutable as well, which makes that if that zip code is accepted, it is a zip code, right? According to those rules. That's very good. Then we know that that cannot change. The validation and the definition of that data is kept together, right? Okay, what else is there? Well, the address object, of course. So we knew that the address object, according to our model, is somehow constructed by the various components. Those tiny building blocks, zip code, building number, street, city, country, and so on. Those cannot be null, according to an address. And then we have a various invariance checks that says validate invariant city, country, street, city, building number, street, zip code, city. And that would of course go against some sort of mapping reference service or something that would actually contain the properties that we can validate against. So if this thing passes, we know that this address is good. This is an okay address, it exists, it cannot be changed. So throughout our system, this address can be sent along, and since it's immutable, we don't need to ever be afraid that it updates, so we don't need ever blocking operations are unnecessary, of course. But this is an immutable object that we can utilize on. And of course, the register code becomes a lot simpler. We're saying that all these various parameters are now immutable value objects. They should not be null, and then we're going to add an address in our repository that is constructed this way. And now we know that this particular address is not only correct from a structural perspective, it's also correct from an invariant perspective. And that's very, very powerful. It becomes very hard to inject stuff then. Right, so the upsides is that we get a tight coupling between the data and validation. Like I said, data and validation are kept together. They get moving around in the system. We also promote whitelist validation invariance checks, because that's how we have defined that particular address object, for instance, right? We also reduce the duplication, because everywhere in our domain where we should create an address, we should create it this way. And since validation and data is kept together, well, if you change that validation, it changes everywhere, right? And it also helps us to prevent that second-order security weakness that I talked about. But what are the downsides? Well, the downsides are actually inherited a bit from domain-driven design. And unfortunately, involving business and domain experts may seem tedious. There are some places where they don't like this. And the fact that it may seem less flexible, because you have to ask them, so how long can a street name be? And they go like, what? It's just a street name. No. Is it max 100 characters? 200? 300? What's the maximum? And they go like, oh, well, I don't know. How does the building numbers look like? Are they 2 numeric values and then followed by a character? A to Z? A to F? What is it? And they have to think about their domain, and then they have to, come up with a good answer, because you are going to add those in your validation logic. So that may seem a little bit less flexible, although you're doing the correct thing. And then, unfortunately, you're going to run into problems with test data. And this is so funny. all suddenly, you had this code with using all those strings everywhere. And it turns out when you added that validation logic and that strictness, all suddenly that test data is no longer compatible because it was partial. It contained null fields, or it contained incorrect street names, or could be, you know, swapped in certain ways and so on, because it's just test data, right? Nobody really cares about it. And all suddenly you have a problem that you need to clean up your test data and make it correct from a domain perspective. So now you're all thinking, wait a minute, I learned this, you know, back in the days, that we should use prepared statements. I saw a SQL injection that was prepared. Should we just ignore that now? I mean, since we can use this DDS thing, so we map everything to value objects? Well, the short answer is no. You should not remove your prepared statements. And the longer one is, of course, that prepared statements is actually an excellent way to separate syntactical constructs and data. So we should, of course, keep them and use them every time we interact with our persistent context. Right? And since we're about context, we move over to the next thing. And that's, of course, cross-site scripting. And if you look at the documentation about cross-site scripting, you can read about it, and it says like this. Cross-site scripting flaws occurs whenever an application takes untrusted data and sends it to a web browser without proper validation or escaping. Cross-site scripting allows attackers to execute scripts in the victim's browser, which can hijack user sessions, deface websites, or redirect the user to malicious sites. And the key essence in this is actually that untrusted data execute in the browser. Once again, you go like, wait a minute, I just learned a few seconds ago that we can map all our untrusted data to domain objects and we're all fine, right? So when I thought about this, and I thought about the domain-driven security, I'm like, what kind of example should I come up with so I can illustrate that that's not enough? So I came up with this. Or, sorry, forgot about that. We have to look at the bounded context. And you heard about this in Sam Newman's talk about microservices yesterday, that bounded context is a way to separate large domains into separate distinct ones that are focused on what they do, right? And I know Eric Evans talks about bounded context nowadays and views them as this is the perfect boundary for a microservice. Anyhow, by analyzing how the various bounded contexts are interacting with each other and how they are mapped, you can get a notion of how data flows between these different contexts. And that turns out to be a significant part in understanding how we can prevent cross-site scripting. And now we come in to my example, and that's the coder's blog. Because in the previous example, we said, wait a minute, if I get address data, I should not accept, you know, script 42 or alert or some, you know, JavaScript that you inject in there. But on a website where you're supposed to ask questions about code, that's really not an evil input. It's actually the good input. So how can we prevent from accepting evil code from good code? This is the worst example I could find, right, or come up with. So the question is, can we avoid cross-site scriptings now? Well, as it turns out, a cross-site scripting works this way, and this is a stored one. And that is that somebody, the yellow guy over there, adds a question about, what does this mean? Script alert 42, right? So they enter that on the blog, and it gets, you know, stored in some database or persistence layer. And then you guys come along, and you're real good at this, so you can answer questions on this blog. And you see, like, wait a minute, what does this mean? And all suddenly, that alert box pops up in your browser window. It says 42. And all suddenly, what we have succeedingly done is that we have stored a script that gets executed in your browser. Remember the definition? Untrusted data executes in the victim's browser, in your browser. So how can we prevent that from happening? Well, we won't be able to map that to a domain object, right? Because that's the data. Instead, what really happened is this. If you do context mapping, you start realizing that when you add your question, you're in a right context. In this context, it's supposed to be code. This is really what you ask about. But as soon as you read this and you render this in a browser, you're in a read context, and now it should be treated as text. But doing this context mapping between these different worlds, you start realizing that we can just accept the data coming from the write context to the read context, because then we can get that, the browser will interpret that as code. So to prevent us from doing this, we need to do this context mapping, and we need to do proper escaping. A lot of frameworks out there do that. Unfortunately, there are some that don't. And well, sometimes people do this by mistake as well. So basically, by understanding that the data travels between these contexts, we can get a notion that this actually is happening. And then cross-site scripting is therefore a broken context map. Okay. So we all heard about Hadi's talk. He was chasing that silver bullet in the keynote, right? So of course we're going to bring in the reactive manifesto in this talk, because we're also chasing that silver bullet for the perfect secure application, right? So then you might wonder, like, why are we bringing in the reactive manifesto? Well, there are actually 3 parts in here that are really interesting. And those are, first the one is responsiveness. If you read about it, it basically says this, that the system should respond in a timely manner, and it should deliver a consistent quality of service, if possible, right? This is very interesting, because an attacker is trying to make your system behave strangely, right? Another interesting thing is resilience. And that actually states that it should be responsive in the face of failure, and failure should be contained. Okay, interesting, that's good. A third thing is that elasticity, right? In case we add a lot of workload to our system, we should not have any contention points or central bottlenecks. Our system should be up and running and handle that, right? So then you're going to go like, oh, wait a minute. What does this really have to do with security? I mean, these are good design patterns, right? Or properties of good systems or reactive systems. Well, as it turns out, it's all about feedback. Hacking a system is really about feedback. If somebody attacks your system, they want it to behave strangely, right? Because then they will get clues about those internal vulnerabilities. They will realize that, wait a minute, I injected this thing and that thing came out. Maybe they have a weakness here. Maybe it behaves that way. So let's look at some good craftsmanship patterns, because we have our hypothesis that we're trying to prove, right? And the first thing is circuit breakers. You all heard about this in various talks now. I mean, Sam talked about it, Hadi talked about it. It was also mentioned in Josh Long's talk. But circuit breakers are really awesome. And Michael T. Nygaard presented this in his book, Release It, back in 2007. And it basically is a way to protect our system from hogging another endpoint, right? So if you think about this from a security perspective, is that if somebody, attack your system with a lot of strange stuff, and it turns out there's a weakness in the endpoint system that you have a dependency to, but you added a circuit breaker in between, that other system is probably going to start behaving strangely. And it might get slower and slower and slower, and all of a sudden we should not put any additional load on it. So our circuit breaker trips. Of course, the attacker could make your system behave strangely in the sense that the default method is being invoked instead of doing the correct invocation against that other system. But at least we are protecting that other system from additional injections, right? Bulkheads, that's also an important pattern. And if you guys have used Hystrix, you know that they implement both bulkheading and the circuit breakers is an awesome implementation. But Michael also brings this up in his book, Release It, so definitely read for this summer if you haven't read it. And the basic idea is that we should not let one failure affect the rest of the system. And usually you bring up this example with a ship and there are different compartments, but I think of a car instead. Let's say your lights goes out. I mean, it should not affect your brakes or your steering or anything else, right? You should be able to safely bring that car down to a stop or whatever it is. The same thing goes with software. If something starts failing, you should still be able to continue, right? Of course, in a limited capacity, probably. But somebody cannot exploit your system and inject something. Let's say they DDoS you, and all suddenly you can't, operate anymore. So you should be elastic. You should actually prevent that from happening. And if something goes down, it should not affect the rest of your system. So that's also a very good pattern. Here's actually something that my dear colleague Daniel Savano, which I had a previous talk with a few hours ago, that he brought into our latest project. And that's actually pretty neat. And I would like to call it sensitive value one-time read-only. And what this is, unfortunately you guys in the very back and probably can't read this, but what it is that we have created an object that allows one-time access to the value. And then you go like, what kind of security is that? Well, as it turns out, that if you have a complex system where these kind of data travels through that system, it might be that somebody added let's say a log statement or something. By accident, they actually flushed out that value. And by doing that, they actually expose the security risk, right? If somebody comes over that particular data, well, you're being hacked. So by doing it this way, we're able to basically say that the first time you request this value, you get that value, fine. But the next time, you won't. Actually, a contract will fail. And the thing is that at the place where you expect that data to exist, you're going to get a complaint. So you probably are going to find that there's some illegal access going on in your execution flow. And you need to start investigating where did that happen, right? It's usually pretty easy in IntelliJ or Eclipse or something. Another thing is that you can't compare this value to anything else. Of course, now you're going to say, hey, wait a minute, you're using strings up there. What happens to a string in the JVM? Well, we know that strings are being cached and so on. And of course, if you want to be really, really, safe, you should use a char array. But unfortunately, APIs tend to use strings, and so you have to be some sort of pragmatic about it. But if you could, let's use a char array so you'd be on the safe side. Another interesting thing is if you start writing evil tests. That's also a very good pattern. If you have your value objects, like we talked about in the beginning, you should add tests that basically tries to inject bad data into it, right? And the reason for that is not only to verify that, we don't accept this, you actually start thinking about what kind of bad data could actually enter this, or what should we focus on? We should probably focus on, these good characters or this structure or whatever it is. And of course, in this type of test, you would also have what's valid data. So usually it's quite good to have this discussion with your domain experts or whoever it is and say, okay, which are the good ones? How should it look like? What's the structure of this? What should be accepted? So, and in this one I used the JUnit theories. It's quite easy if you haven't used it before. Stack traces. This is a little bit embarrassing to bring this up in this talk. Just a poll, how many of you display stack traces to your end users? It was the hand like this, I think. Yeah. Well, the thing is that, remember what I said, that everything is just about feedback. And the hacker really, really wants to find out what your internals are, right? So if you look at this particular stack trace, I just took it off the internet. They seem to be using an SQL server, Hibernate, Tomcat, Spring, fairly standard stack. But you will get surprised when I say that there are so many evil web sites out there that would say, oh, which version are you using? Oh, here, download this recipe of various exploits that are in there, and you can run this script, and now you can attack that site. I mean, it's insane. There's a small tear coming in my eye when I see those, because as a developer, I really want to make good software and everything, and all suddenly somebody publishes this, and I go like, what? I use this component, and all suddenly I have this security flaw in there. So what should you do? Well, you should not display your stack traces, of course. And there are various techniques to do it, and it should be something like this. And it should be, of course, a message saying, oops, this is embarrassing, or whatever, it seems to have made an error. Because it's not the fact that you're hiding that you made an error. Apparently that happened. And that's terrible. But you should not reveal to the hacker or whoever did what your internals are. That's extremely important. Right? All right, so legacy code. How many of you have crappy legacy code? I think there was one hand that wasn't up. Yeah, that's good. So the thing is that when you look at legacy code, you start realizing that, wow, this is something that we usually don't want to touch. And the question that arises is that how can we start working with this without, having to rewrite the entire thing? And the thing is that by adding the stuff that we learned so far, it's quite easy. You start carving out, like you would do with a microservice. If you're going to move over from a monolith to a microservice architecture, you usually tend to start with, this little relationship between these different classes, we can extract them into a component, and then we can say that this one is protected from the rest, and we have some sort of algorithm that either goes to the monolith or goes to the microservice. And the same thing goes here, that you should be able to extract that particular code, and you say, inside of this component here, we are going to apply all these various tools that we've learned so far. And we're going to treat the legacy code as something that we cannot trust. So every time data comes from that, we are going to revalidate it, and we're going to treat it as a false general. And by doing it that piece by piece, we are eventually able to get a lot of either microservices or whatever you have extracted that are fairly safe. Right? But please do not misinterpret me. Doing this is painful. Legacy code is legacy code. It's just going to hurt. It's going to be expensive. It's going to be tedious. But that's the only way we can deal with legacy code. It doesn't, by some sort of magic, becomes good code. So you have to work with it. Usually when you start looking at legacy code, you run into this type of problem. Cyclomatic complexity. That's something that was published by Thomas McCabe back in 1976. And it basically is a measurement of the number of linearly independent paths through a program's source code. Right? So if you look at some code, you could look at something like this. And there are various different paths through this. And the thing is that when you have a lot of execution paths inside of a code block, that means that it's going to be more complex, right? You probably need to test every path, most likely. And you probably are going to be a little bit afraid when you start changing stuff inside of this code block, because there's so many different paths. Am I sure that this is being executed correctly? Have I covered everything? So the chance for making a mistake inside of code with a high CC value is actually larger than making a change in a piece of code where the CC value is lower. You could probably agree to that. And if you look at this code, it turns out that this code is the same thing, believe it or not. And this one is a lot easier to grasp. And it turns out that this is a room reservation algorithm. And well, you all know how it is when you book those meeting rooms. It tends to be overbooked, or there's some sort of clash. So apparently this is very complex. But this piece of code basically says, here's a meeting, here's a room. So we have used our domain objects. We have injected our immutables. And we basically says, okay, let's store this booking, and we notify our invitees. And if you look at this old code, this seems to do the same thing. And yeah, that takes a lot longer to read, and it's a lot more difficult to understand. And usually when you start editing this stuff, you can make mistakes, and that could open up for security weaknesses. So what are the key takeaways today? Well, first of all, designing software is difficult. I mean, seriously. Designing software back in the 70s, even though I didn't do it, I believe it was a little bit simpler. Please don't hurt me. No. I believe that was simpler because the fact that you did not push your application into the cloud. You did not have this elasticity thing. You did not have transactions 24/7. Your end users across the world, and so on. Of course, you had other problems, right? And another takeaway is that security seems to span across your entire application, right? It's something that goes against the fact when you do development. When you do development, you tend to go from the top to bottom, right? You fix it, you're like, oh, here's in the UI, I'm supposed to add this and that, and it's supposed to go down to the persistence layer and back up, or whatever. So it's another dimension of software development. And the thing is that we as developers, we can't think of everything. So therefore, we should add these good design principles and adhere to them. And by that way, we make security a natural part of our application and development. That's actually pretty interesting. If we adhere to the patterns we found in the Reactive Manifesto, if we use domain-driven security or even domain-driven design, and if we treat sensitive values that way, if we do all those things, which is good design, we like to do the good design, all suddenly we have made it a lot harder to inject stuff and to exploit this application just by doing it that way. And that's nice. So then we can actually start focusing on good design and not on security as a separate task. So back to our hypothesis. And you all seen Mythbusters, right? And they say, well, is this false, true, or plausible? And I'm not really sure that I can say this has been proven. But I can say that it's plausible. This is most likely the case, that adding these good design principles prevents a lot of security flaws. And the thing is that I've been in various projects, and in my current project now, we're actually doing security penetration tests. And the funny thing is that this project is actually a result from a previous version of that system. And that system had so many security issues and problems that they decided to shut it down. And they gave me, among other people at Omega Point, the chance to design a new one for them. So what did they do? Of course, they wanted to have these security penetration tests because we say, hey, we can develop software that's safe. And they haven't found any security issues. I don't know if that's a good thing or not, but that turns out to be the case so far. We worked 1.5 years on it now, which is kind of easy, interesting. So hopefully this hypothesis is true, which means it will be a lot easier for us developers to add security to our code. And yeah, I think that was it. So we have time for some Q&A. Oh, so the question was that designing software with security in mind is, of course, quite challenging. And the question there was that, are there any products that will help you find these kind of security issues out there? The quick answer is yes. The longer one is tougher. Shoot, I can't remember what they know. I mean, usually the penetration testers know about it. I mean, they have this entire portfolio of things, and they apply this. And there are also various static code analysis tools that can, find potential security weaknesses and so on. Unfortunately, I have to say pass. I can't name any ones. Sorry. Yes. Okay, the first question, let's start with that one. What does elasticity mean in the terms of Reactive Manifesto? Well, the thing is that if your application is being DDoSed, so there's hundreds of computers or clients accessing your service, right? So that basically is going to make your system halt or not stop working, unless you have implemented elasticity patterns, which makes that if you're in the cloud, for instance, you could make sure that new instances are automatically booted up, and then you can meet that sudden demand. And all of a sudden it becomes a lot harder to DDoS your application. I'm not saying it's impossible, but I'm saying it's a lot harder. And well, that's the answer to that question, I would say. And the other question was that when do we do escaping when we do when data travels through different contexts? And it really depends. In the right context, like we saw in my example, we probably shouldn't do any escaping because we don't need to. We don't interpret that value anymore. It's just data. But when as soon as it hits the read context, we should probably escape it. It could be at the very beginning in that entry to that context, or it could be at a later stage, depending really on your implementation. But the important thing there is that we should do escaping. Yes. Yes.
How real is example with address about, I think about invariants. If you want to check all invariants, you have stored them.
Yes.
About streets, numbers, there can be new streets, numbers, new buildings.
So the question was that how real is this example about addresses, and how do we do these invariant checks, because there could be new addresses all suddenly. And for the first part of that question, I would say, no, this is not real. I made it up, of course. But the second part is that, yes, there are domains where we actually work with addresses. And I worked in a company in the gaming industry that were using addresses as a way to identify if you wanted to be part of that lottery or not. So, of course, the problem of having a cache of valid addresses compared to what reality offers is a problem. But it turns out that addresses tend to be quite fixated. They tend not to pop up, so you can refresh your cache every day or whatever it is, and that should be fine. So yes, so that part is actually real. Yes.
You mentioned that you have security testing, and what kind of vulnerabilities you are testing? Just this 10 from list, or you have just another list?
So the question was that what kind of vulnerabilities are we testing for when we're doing penetration tests? Well, of course, it really depends, of course, on the project that you're working in. What kind of security requirements do you have? Are you testing, is it a web application? Should we, try to prevent all the OWASP top 10 issues that have been found? That's actually part of my current project. And of course, the penetration tester would then use tools that would, try to attack your application according to those things. But there could be other things that depending on your application, there could be weaknesses in the JVM, or it could be weaknesses in the Java language itself that you're trying to exploit. So it really depends on the domain that you're working in. Any more questions? All right, thank you very much.